So, good morning, and let's resume from the previous discussions. So, last class, we have already discussed the recurrence trees to be solved. So, recurrence relations to be solved using substitution method. Solution we have discussed using first method as a substitution method, and today we are going to talk about the recursion tree or recurrence tree to be used. So substitution method we last time talked based on good guess we have to do, and it is a guess based, intuition based, and smartness also needed, smart and correct guess needed. So not always easy, and even if we are able to do that, then proving will be another aspect needed. Proof using this, and sometimes proof doesn't become possible. So all those problems are there. So obviously we are going to see some better methods. Of course, last time we talked of one example where some students had a doubt. So I'll just quickly touch upon that. We said that if I have a relation like this, plus we have 2t, what was that value is plus log n. So if I have to solve it, I said substitute or change the variable by saying n equal to 2 raised to m. So effectively this becomes a t of a 2 raised to m equal to 2t m 2 raised to m and a square root of that plus log of a 2 raised to m, effectively becoming that a 2t 2 raised to m by 2 plus m. Now I can easily say, if I say that I am talking of a 2 raised to m as a variable size, here the size is reducing. So I can now probably reach towards a good guess. For example, I will simply say, assume t of 2 raised to m equal to some other recurrence relation s of m in terms of m. Then I can easily see this is nothing but s of m into 2 into s of m by 2. Earlier it was for 2 raised to m. Next time it became 2 raised to m by 2 as a recursive relation. And then m remains m. This can be guessed correctly. So it will be guessed correctly as, of course, order of m log n. So I can easily see that I will be able to have m log n. This is a simple merge sort with similar relationship. So I can easily guess it as m log n. And so I will say ultimately I will be able to solve it as Sm will be effectively nothing but I am able to solve it as m log n. Order of m log n. Substitute back. Let this be considered as a 2 raised to m. So S of m effectively becoming nothing but t raised to m equal to S of m. And this I am able to have it as m log m. What is m? Now go towards n. So let's say go back towards n. This means m equal to log base 2 of n. So I will say t of n2 will be nothing but log 2n, log n into log of log 2n. So I can easily say that this is how it will be solved to get the corresponding answer. So this is how you will be solving situations like this. Not a big issue. There was some doubt with some students. So I just wanted to complete it quickly. But today's focus, a more generic and more useful method, which we call as a recursion tree. Last time I used the word recurrence tree, but in the textbook also the word used is a recursion tree. So let's use it with a proper word. We say that now we are going to make it as a tree where recursion will get solved. So it's a generic and systematic method and could be useful for most of the problems to be solved. No guess needed. So you can systematically and mathematically, logically solve it. For example, I take a relation that if I have Tn equal to 3t n by 4 with a floor plus Cn square, say solve it. First thing is, we have already seen that floor and ceiling, etc., don't make much difference, because later I will be able to convert that to a less than equal to symbol. So they become insubstantial. Hence, we need not bother much about that. Moreover, asymptotic complexities are approximation. All asymptotic complexities are effectively approximation. So one small value through floor and ceiling don't make much of a difference, and we will be not going to bother about this. So simple rule will be, don't bother much for these. You can ignore these without much of a difficulty. That will mean I can effectively consider Tn to be equal to 3t n by 4 plus Cn square. Now, this I will solve by making recursion tree. And by making recursion tree, I will always mean that it will have a root and some children. Children will be effectively nothing but the recursive calls with reduced size, obviously. Like in this case, here I have 3 recursive calls, each with the size n by 4. And root will be the non-recursive contribution. For example, in this case, I have already seen that contribution to be Cn square. So I say, for a tree, for a recurrence relation like this, I will draw it as Cn square plus Tn by 4 as one child, Tn by 4 as another child, and Tn by 4 as another child. So I say my total complexity will be nothing but, I can easily say it will be nothing but summation of root and all children. This is what is there. And all children. So I can easily see my total contribution is a Tn by 4 plus Tn by 4 plus Tn by 4 plus Cn square. So my overall complexity is the same which I have just written earlier, Tn by 4 plus Tn by 4 plus Tn by 4, and of course plus Cn square. This is still now correct. The purpose is this itself can become further a tree. So I will keep on expanding this tree and solve mathematically one by one. What does that mean? I said it was a Cn square, Tn by 4, Tn by 4, and Tn by 4. But Tn by 4 means it's again a recursive word. So this again to be replaced in the similar manner. So I will say, let this be replaced for effectively Tn by 4 means nothing but it means 3t n by 4. Earlier it was written as this 3t and whatever n plus c n by 4's whole square. Replacing n by 4 into the Tn. Tn was 3t n by 4. So now n itself is n by 4 divided by 4 plus this. Effectively it means 3t n by 16 plus c n by 16's square. So this was n by 16 and n square by 16. So effectively it becomes c n square by 16 and Tn by 16, Tn by 16, Tn by 16. Similarly here, I will say this will become again substituted in the similar manner. Substituted means this becomes a Cn square by 16. Once you have a Cn square by 16, this I will become sorry, this I will just wait a second. So we were saying that, yes, this is there, Cn square by 16. This will further have similarly 3 children, each with a Tn by 16, and so and so. Here also the same replacement will happen. This will become Cn square by 16, and again 3 children. Let's just look at one of these child, what this will become, and then probably that will become a good mathematical way of solving this. Tn by 16, I'm just removing this so that we can write clearly for one of them. So I say, if I have this, this will further mean the same Tn by 16. Cn by 16 will mean assume and calculate Tn by 16. So Tn by 16 is nothing but 3T n as n by 16 divided by 4, plus we had Cn square. So I can say n by 16 square. Now n is n by 16. So 3T n by 4 and Cn square. So n is n by 16 here, that I did. Effectively, what does this mean? This value will become Cn square by 16 square. This will also become Cn square by 16 square. This will become Cn square by 16 square, and so everywhere. Total, effectively, I have 9 times because there are 9 children, and each of them further becoming T of n by 64, or effectively n by 64. So you can say earlier I had here this, and accordingly it will keep on rising. So now I can easily see what is becoming. I want this ultimately to reach to T of 1. Why I want ultimately to reach T of 1? Reaching T of 1 has non-recursive or no tree needed. And T of 1 is guaranteedly 1. So I will finally say, finally this will reach to value 1. There will be, these will become leaves, and leaves will not further grow. So all leaves, many leaves will exist. Each leaf contributes value 1. Each leaf, I'll say, contributes value 1. So effectively what I am going to see is, now you can easily see I have a Cn square at this level. Then I had C into n by 16. Let's see the previous one. Yes, Cn square by 16. Cn square by 16. Cn square by 16. Next level I had C into n square by 16 square. This also Cn square by 16 square, and so, finally reaching to T of 1, which is equivalent to 1, and these are leaves. So now I say I have 2 kind of solutions. I will say level-wise summation to be found, and that will be a mathematical relation possible. So level-wise summation will make some mathematical series. How? Let's see. This summation is nothing but a Cn square. This summation is C into 3 by 16 Cn square, or I'll say Cn square into 3 by 16. So I write it as Cn square into 3 by 16, because this has 1, 2, 3 total values. Here I will get Cn square obviously, and I am going to have 9 values here. 1, 2, 3 from here, 3 from here, and 3 from here. So effectively this will become 9 by 16 square. Instead of 9, I just try to write it as a 3 square. So effectively it is equivalent to saying that this 9 by 16, because it was 9 by 16 square. So I wrote it as this. Why did I write? Next time this will further have 3 children. This will have further 3 children. Total there will be 27 values. And downwards factor will become Cn square divided by 16 raised to cube. You can see here it was Cn square raised divided by 16 raised to 0. It was a Cn square 16 raised to 1. Next level was a Cn square divided by 16 raised to 2. Next level will automatically come Cn square divided by 16 raised to 3. And there will be such 27 values. That summation of this level will mean Cn square into 3 by 16 cube. Downwards is a 16 cube and above is a 27, because I have 27 by 16 raised to cube Cn square. So I can say this. And then there are going to be some levels. So now the question is, if I assume this is level 0, then this level I call it as level 1, level 2, and some level k will come when recursion will stop. So I should know what is a k. So I say level 0, I say level 0 to level k minus 1, the values are Cn square divided by 16 raised to something into something. Cn square by 16 as level 0. Then I have 3 by 16. First level was Cn square. So then I have 3 by 16 into Cn square. Then I have 3 by 16 square into Cn square. And so and so. And then I say level k has leaf nodes with value 1 each. How many leaf nodes will be there? Accordingly, I will say those many nodes into value 1. So this values into 1 will become contribution of level k. So my contribution of level 0 to k minus 1 is in terms of a Cn square into something, and contribution of level k will be 1 into total count of leaf nodes, because leaf nodes not contribute as Cn square 3 by 16 Cn square. Leaf node is guaranteed the non-recursive. Non-recursive value t of 1 is 1. So I should know how many nodes are there. For that, I should know what will be the k. I want at level k, we got t of 1. T of 1 means effectively it became t of n by n. And this was growing as n, then n by 16, then n by 16 square. So that means at level 0, we had t of n by 16 raised to 0, level 0. Level 1, we had t divided by n raised to 16, 1. Up to level k minus 1, it will be t divided by n divided by 16 raised to k minus 1. And level k, it becomes a t by n divided by 16 raised to k. 16 or this. So we can easily see that this is what is going to be there. So initially I had a Cn square, and then we had Cn square by 16 or 4. Let me just check. I think we did some mistake. So first level was a Cn square. Next time I said that this is going to be 3Tn by 4, and then accordingly, let me just check that whether I am. So what we were doing was already, let me just, yes, so sorry, due to some network issues, the connection got temporarily stopped, so I'm restarting. So we were saying that now we have got these level-wise summation series to be done. So effectively, level-wise, I have to see, and total levels 0 to k minus 1, we have already seen this to be considered, and level k to be considered leaf. So k I have to find out. So let's go back and see what we were doing. Here we have done calculations. So first time it was Cn square. Next time it is Cn square by 16. Next time, I think we did some mistake in noting down. This was n by 64. So this is not a 16 square. This was effectively, I have to probably write correctly. I am not able to correct that. It was Cn square by 64. This is a 64. This is a 64. And accordingly, I have the total available. Next time, I'm going to call it as for n by 64. So corresponding to that, it will be accordingly done. So I can easily say first time it was n by 60. Next time it was a 64. This was a 64. So I can easily see that this was going to be summation correspondingly. And next time I am going to have 64 into 4 every time, because this is further divided by 4. This was here effectively Tn by 4 every time to be as a child. Let me just not write here. From this, every time it was Tn by 4. So n came here as n by 4 from here. So n is replaced as correspondingly. So I go for the corresponding value as n by 4. This became 4's square. 16 effectively meant that 4's square. So effectively n was replaced as n by 4. Next time n by 4 will mean further n by 16. So accordingly, let me just quickly redraw it, because now it will be easy. So I said initially it was a Cn square. Then we had it as a T of n by 4. T of n by 4 will mean that I am going to replace it with 3 calls to Tn by 4. 3 calls to Tn by 4 will effectively mean that n becomes n by 4. So it is C of n by 4 square, C of n by 4 square. This becomes C of n by 4 square. Next call, next to this is going to be 3 calls, where effectively n becomes n by 16. So effectively this will become n being replaced n as n by 16. So this will effectively become n by 16 square, and like this. So, and having 3 children, 3 children will mean that you have effectively 3n by 64, because n becomes a 16, n by 16. So Tn by 64, Tn by 64, Tn by 64, and again n by 64 will be replaced. Replaced will mean that now I am going to have this correspondingly as taken C n by 64's square. So accordingly, now you can easily see this is how it will grow. So like this it will grow. It will mean that effectively how my level is growing. Level 0, I had values n by 4 raised to 0 as a square. Next level, I had values with n by 4 raised to 1's square. Then level 2, I had n by 4 raised to 2's square. And similarly, we will reach to some level k where it should become n raised by 4 raised to k as a scale. But scale will not come. Level 4 means effectively it meant to become t of n. T of n is finally replaced as a scale, but because the t of n is becoming 1 and it became as t of 1. So just I think on the last slide, I was writing it slightly incorrect. Ideally, this should mean this was level 4 raised to 0. This was 4 raised to 1. And then finally 4 raised to k. But at this point, it will become t of 1. Summation of the parallel sides, level sides, we have already done. That was correct. So now what should be k? So corresponding to this, I can easily say n will become equal to 4k, meaning that k is nothing but log 4n. So I can say level 0 to level k minus 1 are non-leaves, level-wise summation to be found, which is effectively something as 3 by 16 raised to some power into Cn square. For level 0, it was power 0. For level 1, it is power 1. Level-wise summation. So this is for each level. Why? Just have a look on the previous contributions we have discussed here. So I said this level summation is a Cn square into 3 by 16 raised to 0. This is a 3 by 16 raised to 1. This is 3 by 16 raised to 2 and so on. So I can easily see for level 0 to level k minus 1 summation, each level contribution is nothing but each level contribution is 3 by 16 raised to I, where I will be ranging from 0 to k minus 1 into Cn square. But leaf levels are considered always different. Leaf level means T1 counted number of leaf times. How many leaves are going to be there? We should know that. So T1 will be 1 and 1 to be added number of leaf times. So how much is this count? Let's try to see that. How the count is growing, now I can easily say. First time count at the level 0 is 1 node. Next time nodes became 3. Next time node became 9. 3 nodes. I have 1, 2, 3. Next time 9 nodes. Next time at 27 nodes. So effectively, my nodes are 3 raised to I. Level 0, 3 raised to 0. This is 3 raised to 0. This is 3 raised to 1. 9 is equivalent to saying 3 raised to 2. This is equivalent to say 3 raised to 3. Similarly, at level k, it will be 3 raised to k at leaf. At level of the k, 3 raised to k nodes will be total in total width ones. So I can easily see this count is going to be 3 raised to k, and k we have already found. So T1 is, I can easily say, contribution of leaf level will be now computed separately, and contribution of leaf level will be equal to T1, which is 1, multiplied or 1 added 3 raised to k times. So effectively, this is 1 added 3 raised to k times. Because total 3 raised to k leaves are there. Each leaf contributes 1. K I already know. k is nothing but log 4n. So I can say this becomes 1 into 3 log 4n, which mathematically, if I am correct, can be written as n raised to log 43. I say this is nothing but n raised to log based 4 and 3. This is mathematically you can prove. Mathematically you can always find this relation. So I say my total time complexity will be always taken as contribution of non-leaves, contribution of all non-leaf levels, plus contribution of leaf level. Leaf has because T of 1, so that is counted separately. All other leaves contribute something like Cn square into something, and that is why we find those summations alone. And mathematically, total levels we have calculated. They were total 0 to k. Out of those, 0 to k minus 1 are non-leaf. So I can say non-leaf or non-leaves, you say. So I can say total time complexity equal to summation of I equal to 0 to k minus 1. That effectively means non-leaf level I's contribution. Each level's contribution of non-leaf to be added, plus leaf's contribution, which is nothing but n raised to log 43. I can easily now mathematically solve this. We have already calculated. This is nothing but 3 by 16 raised to I Cn square. How? We have just calculated this value of each level's contribution as 3 by 16 raised to I. You could easily see that how did we get that value is here, that this was 3 by 16 raised to 0, then 3 by 16 raised to 1 Cn square, then 3 by 16 raised to 2 Cn square, 3 by 16 raised to cube Cn square, and so on. So based on that, I can say this is my total contribution plus n raised to log 43. Now I have to solve this. So this 3 by 16 is a kind of a GP series. You can calculate its summation will be A, that is 3 by 16 divided by 1 minus 3 by 16 raised to n. N means k, total number of terms in the GP series. So in the GP series, I can easily find something like this, plus n raised to log 43. But further how to solve? And into Cn square is already there. Now what? Not easily solvable. I am not able to reach to some quadratic equation, etc., or real equation, or where I can simply say that now I can find out big O. No, I am not able to. So I will say, instead of writing it like this, I said my Tn is equal to summation of I equal to 0 to k minus 1, 3 by 16 raised to I Cn square plus n raised to log 43. I will say as 3 by 16 is less than 1, treat it as infinite series and use inequality of less than equal. Have some extra value added on the right side. I can say Tn will be less than equal to previous summation plus some additional terms. Additional terms will bring I to go from 0 to infinity. and additional terms added will make that less than equal to, I can write Cn square plus n raised to log 43 is already correct. So I say treat as this is there, I treat it as this. Then I can subsequently write that this becomes nothing but a upon 1 minus r. So a is a 3 by 16 raised to 0. That will effectively mean 3 by 16 raised to 0 is 1 into Cn square divided by 1 minus a or 1 minus ratio. Ratio is 3 by 16 every time. This one is 3 by 16 raised to 0. A is initial term. A is 3 by 16 raised to 0 Cn square. And common ratio for the GP series is 3 by 16 every time. So for a GP series, I can easily see infinite GP series. This relation I will solve and plus n raised to log 43. So I can easily say this becomes nothing but effectively 16 by 13 Cn square plus n raised to log 43. I can say that it is nothing but 16 raised by 16 Cn square plus n raised to log 43 is less than 1 because log base 4 and value is a 3. So it is going to be something around 0.8 or approximately you could say 0.8, 0.9 or whatever. Once I have this equation, then I can easily see that this is going to be the term which is going to be dominating, and this is much more than n raised to any 0.8 or less than this. Had this factor been greater than 2, then this term will become the dominating. But if greater than 2 had been there, only then. Otherwise, I can say this is the dominating term. So I can easily say order of Cn square becomes my time complexity. So using recursion tree, this is how we calculate recurrence solutions or recurrence relations solution. So what quickly we did, I'll just repeat that whenever you have a recurrence relation available, recurrence relation always has two parts. One is, I say Tn equal to some recursive parts, recursive calls written as a T of something, and many calls could be there, plus non-recursive, some terms of some non-recursive value. This value will always become at the root. So you will have root here taking this value and then have multiple children for each recursive calls. Multiple children, I will say 1 for each recursive call with the corresponding size, and reduced size is guaranteed. So that initially is a T of n by reduced size. Then replace this also as a tree. As a tree. Keep on replacing, reach to T1. Find total number of levels needed to reach T1. Once you know total levels, then I will say my time complexity will be nothing but, before that even say, I'll say before going to time complexity, then I will say find summation of each level as that contribution. So leaf level is going to be always 1 into count of leaf nodes. and non-leaf levels, you will always be able to find some mathematical series, and you will say summation over I equal to 0 to the non-leaf level count. And this series term will be there. Then you will try to convert it into a less than equal to by taking it towards infinity. Of course, if ratio is less than 1, only then we can do this, know mathematically. So if ratio is less than 1 of the GP series, ratio of a GP series is less than 1, then I will be able to take it to infinity, plus I will have the correspondingly leaf contribution. And I will solve it. Finally, I will have some terms in terms of n power, say I will have some constant into n power a plus some other constant, maybe c2, with n power less than a, maybe plus c3 into n power even less than, much less than a, etc., etc. Then I will say this is the dominating term. So I can say time complexity for the upper bound will be big of n scale. And recurrence tree, etc., useful to solve it for, or recurrence, or I'll say recursion tree to be more precise. I will say recursion tree method useful to find either upper bound or lower bound also. You can accordingly find useful for finding upper bound, for computing mostly upper bound, so that you can have the series accordingly taken towards infinity, etc. Sometimes you can be able to find out maybe for lower bound also, but of course finding in the single step theta will not be done. So theta notation or exact bound is not done, exact bound not in one step possible. You have to probably guess both separately, not possible in one step. So primarily use of this is that either use it to find upper bound, which is most of the time done, and otherwise you will be able to separately calculate the lower bound and upper bound and then accordingly get the notations. With this, I think we can stop, and this will make the clarity. You can probably go into the book and try to solve some more problems given in the book. In the tutorial, I am going to give you some exercise problems. In the book, there are given many questions. Let me just say, share with you one final certain questions which you should practice. So for your practice, I will say that solve certain problems 4.4-1, 4.4-3, and 4.4-4. These are given on the page 92 and 93 of Corman's third edition. In second edition, the page number will change, but you must practice these and practice many more. So this will give you a good confidence to solve using substitution method as well as using recursion tree. Next class, we are going to talk about the master theorem. Bye-bye. All the best. Enjoy.